So using TD learning to do off-policy Q-learning has some disadvantages to it. Specifically, there's one well-known issue that is known as the maximization bias in Q-learning, right? In off-policy Q-learning. And I'll show you this through an example. I'll show the issue through an example, and then we'll discuss a way to address it. So let's consider the following MDP, the one depicted here on the bottom right corner. So it has two terminal states, A and B. An episode starts in A with a choice between two actions. You can either go left and right. The right action transitions immediately to the terminal state with a reward and return of 0. The left action transitions to B, also with a reward of 0. From B, there are many possible actions, all which cause immediate termination with a reward drawn from a normal distribution. Okay, and that normal distribution has a mean of some negative value, lower than 0, specifically minus 0.1, and variance 1. Okay, but this is just for the sake of the example. The important thing here is that going to state A has a deterministic reward, a very specific reward, while going to state B has a noisy reward that is actually worse than the deterministic reward we can get by going right from A. And so the expected return for any trajectory starting with left is minus 0.1, right? That's the expected value that we're going to, or that we should expect. And thus taking left in state A is a mistake. That's always a mistake. And now we're doing Q-learning by, we're trying to do online learning, reinforcement learning. So we would like to learn these approximate values, approximated Q values, through interaction with the environment. So let's say that so far we observed 4 different episodes. One time we went from our initial location A, we went right, and we got the expected reward, the true expected reward, the deterministic reward of 0. And then the 3 other episodes, we actually went left, and then we saw, as we expect, some distribution over our reward. But this is a very specific distribution. I actually chose these values to be a very good representation of the actual distribution, right? So one time I got exactly the expected value, the mean of our normal distribution. One time we observed one standard deviation less than the mean, and another time we observed one standard deviation above our mean. Okay? So now the question would be, and let's say these were drawn for 3 different actions, and again we can choose from n different actions here at state B. Now the max operator, the max Bellman operator over state B, overall actions at state B, yields a value of 0.9. Why? Because that's the highest value that we've seen so far. Although we know that Q star for B must be minus 0.1. That's the best expected, that's the expected outcome regardless of the action that we're going to choose. Right? In this example, the actions are similar. It can be differently, but in this case you can see that the Q star should be minus 0.1, yet the max Q value is much higher than that. And this shows or demonstrates the maximization bias, right? And you can choose different values or to draw different values here, but as long as at least one time you're going to draw a value that is higher than the mean, well, you're going to suffer from the maximization bias, right? So in the maximization bias, the issue is that some actions will be evaluated following a lower than expected sample reward, and some with higher than expected sample reward. I mean, that's usually what happens. And then we overly rely on those that are higher than expected samples. The max operator biases towards higher than expected sample reward, okay, as we just saw. How can we address that? So the way to address this issue is called double Q learning. So let's see how would that work. So going back to our example, let's assume that we visit state B a total of 60 times, 2 times per actions, assuming that we have 30 possible actions. So let's assume that we visited each action 2 times. And again, our reward distribution comes from a Gaussian with a mean of minus 0.1. And so now, if we are going to evaluate the max Q over these 60 samples, we converge, or usually we get a value of 1.3. I didn't prove that, but this is, I just ran it empirically. I did like 1,000 runs, and on average we get 1.3 in most runs. Which is of course a wrong expected Q value, expected sum of return, right? It should be minus 0.1. So you can see that the bias, if I run it for many runs, it is a true bias, it exists. I converged on 1.3. And so now we would like to fix this issue, and this is what we do with double Q learning. What we do is we store and update 2 independent Q tables. We'll call them Q1 and Q2. For each transition that we sample from the environment, we update one of the Q values and not the other. Choose just one to update and not the other. And then we use one of the Q tables of the Q values for choosing the maximizing action and the other to retrieve the value. Okay, so we separate the process of choosing the action that maximizes the Q value and retrieving the Q value. We separate them and make them independent. So it will look something like that, where we try to compute now the expected Q value by retrieving the Q value from, let's say, Q1, but choosing the argmax over Q2. And this is guaranteed to be unbiased, an unbiased estimation, so I can run this for hundreds of thousands of times, and it will provide me with the correct expected value.